Okay, let's just jump right into this with a fact that I think is going to surprise a lot of people.
Let's do it.
When you think about an animal that can survive without water, your mind immediately goes to the camel, the classic ship of the desert.
Of course. That's the poster child for desert survival.
But that's actually a little misleading, isn't it?
It is, yeah. I
Yeah.
mean, the camel is an incredible animal, no question. But its whole fame is built on its ability to drink massive amounts of water and then just endure extreme dehydration. It absolutely still needs to drink.
Okay, so who are the real champions then? The ones that genuinely, truly live their lives without ever taking a sip.
They're often much smaller, much less famous. You're talking about creatures like the kangaroo rat.
And that incredible ability, that mastery of surviving extreme heat and dryness, that's really the focus of our deep dive today. We've gone through a huge stack of research on life at the absolute limit.
Right, so our mission here is to explore how life kind of cheats the laws of biology in these extreme environments. And we've found it really boils down to two primary and, frankly, ingenious strategies.
Okay, what are they?
First, you have what we're calling metabolic shutdown. This is the ultimate surrender, but it's temporary. It's the art of just pausing life
Wow.
completely.
And the second strategy.
For the animals that can't just stop, the ones that have to stay active, we're looking at hyper-efficient water management.
Which sounds like it covers a lot of ground.
It does. Everything from advanced internal plumbing and waste systems to, and this is amazing, using fluid dynamics and just pure geometry to pull water right out of thin air.
Let's start with that first one, pausing life. The term for that is estivation, right?
Exactly. Estivation. It's defined as a state of reversible metabolic inhibition. It's often called the purest hypometabolic state, and it's actively triggered by stress. So high temperatures, drought, a lack of food.
So it's more than just hibernation for a hot climate.
Oh, much more. It's a full physiological retreat.
And what really fascinates me is just how widespread this is. Dormancy isn't just for bears. It can last for days, for months, or in some cases even years. It's this radical biological flexibility.
The range is incredible. You even see it in marine animals like the sea cucumber.
Sea cucumber.
Yep. Pastachopus japonicus. It can estivate for up to 100 days if the water gets too warm. And to save energy, it stops feeding. And its entire digestive tract just works itself. It undergoes degenerative atrophy.
Wait. Its digestive system just dissolves, and then it reconstructs itself later.
It does. It completely restores itself when conditions improve.
That's not just sleeping through a dry patch. That's hitting a reset button on your own internal organs.
It is. And we see similar deep changes in vertebrates, too. There's a long-necked turtle that buries itself in the mud during a drought.
Okay.
And it drops its metabolic rate down to just 28% of normal.
28%.
That's how it survives for 4 or 5 months. Even freshwater crocodiles, these massive predators, will go underground and estivate for 3 to 4 months every single year.
But it's the preparation, isn't it? The things these animals do before the drought hits. That shows this incredible sort of foresight. Let's talk about the African lungfish.
Ah, the lungfish.
Yeah.
It's a master of this pre-planning. To survive the dry season, it burrows into the mud and secretes this thick mucus cocoon all around itself.
Creating its own little humidity chamber.
Exactly. But what's really fascinating is that, well, almost every other system is powering down for months, maybe even years. Its immune system stays fully active.
Why? Why would the immune system have to stay on high alert while the rest of the fish is basically in suspended animation?
Because the skin is its main barrier. And when you're wrapped in mud and mucus, you're just a sitting duck for bacteria and fungi.
Right. So it's targeted maintenance.
It's essential maintenance, while the rest of the factory is completely closed.
And then you have the African clawed frog.
The Xenopus laevis. They dig into the mud and can voluntarily lose up to 30% of their total body water.
30%. Just to put that in perspective for you. If a human lost even 15%, you'd be in very serious trouble. Losing 30%. It should turn that frog into a dried out husk.
It should. It would make its blood incredibly thick, damage its cells. But its muscle and liver cells stay perfectly intact, ready to go.
Which brings us to the real paradox here. The biggest challenge isn't staying dormant, it's waking up.
Precisely. That seems like a huge evolutionary flaw, doesn't it?
Yeah.
The biggest danger isn't the drought, it's the recovery from the drought.
How does that work?
Well, when these animals switch from that super low metabolism back to an active state, there's this immediate huge spike in oxygen consumption.
Okay.
And that sudden rush of oxygen creates a massive surge of these highly destructive molecules.
Yeah.
It's called reactive oxygen species, or ROS.
So it's oxidative stress. It's basically like your cells are rusting from the inside out.
That's a great way to put it. It is a toxic side effect of restarting life.
So if waking up is so dangerous, how on earth do they prepare for that attack while they're still shut down and barely functioning?
They use a counter strategy. The science calls it preparation for oxidative stress, or POS.
So they're getting ready for the problem ahead of time.
Exactly. They enhance their antioxidant defenses before they're exposed to the reoxygenation. They essentially preload the antidote to all that cellular damage.
That level of planning, preparing the cleanup crew before the mess is even made, that's amazing. Can you give us an example of how that preloading works?
Sure. There's a species of snail, Palmacia canaliculata. It doesn't wait for the oxidative surge. It keeps these crucial antioxidant enzymes,
Like what?
superoxide dismutase, SOD, and catalase. It keeps them at constantly high levels throughout the entire dormancy.
So the molecular cleanup crew is just on standby permanently?
Exactly. Ready to neutralize those harmful free radicals the moment they appear.
And you see this in land animals too.
Absolutely. Look at earthworms. During estivation, they switch off the genes for normal metabolism and digestion, but they massively ramp up the genes for antioxidant defense, for DNA repair, and for their immune response.
They're choosing fortification over function while they wait it out.
Precisely. And they also start accumulating a compound called alanine. This does two things. It acts as a nitrogen reservoir, kind of a stored protein bank, during dehydration.
And the second thing,
It can also work as an emergency energy source if oxygen levels get critically low underground. It's this multi-layered chemical defense system.
okay, that covers the stop life strategy beautifully. So let's pivot now to the animals that have to stay active, the ones fighting that constant war against water loss.
Right, the hyper-efficient engineers.
Which brings us back to the champion, the kangaroo rat.
The ultimate example.
So this tiny rodent never, ever needs to drink water. Is its water source just fundamentally different from ours?
Yes, in its application, it relies entirely on what's called metabolic water.
Which is?
It's the moisture that's generated from the chemical process of breaking down the fats, proteins, and carbohydrates in the seeds that it eats.
So it's literally manufacturing its own hydration from its food.
Yes. And on top of that, it lives underground where the air is cool and humid. And crucially, it never sweats. It doesn't even pant. Every possible exit for water is sealed shut.
That's maximum efficiency. But it's not just the tiny animals that can do this, which is what I find so surprising.
No, not at all. Consider the gerenuk. It's a type of antelope in East Africa, sometimes called the giraffe-necked antelope.
And it lives in these dry scrublands.
Right. And it actively avoids water holes, probably to reduce competition and stay away from predators. It gets 100% of the moisture it needs just from the foliage it eats.
And it prefers certain types of leaves.
Oh, yeah. Deciduous trees. They're much more water-rich. They have over twice the water content of, say, coniferous trees.
And like the camel, it has a trick up its,
Mm.
up its nose.
It does. It has these highly adapted nasal passages. They act like a dehumidifier, recapturing moisture from its breath before it even leaves the body.
And then you have external adaptations. I'm thinking of the thorny devil lizard in Australia. That spiky skin isn't just for show, is it?
Not at all. It's a brilliant hydration system. That skin acts like a network of tiny capillaries. It literally absorbs moisture right out of the air, or it collects dew and rain.
And channels it where?
Straight to its mouth through these tiny grooves in the skin. It's using physics and texture to passively pull water from the environment.
Okay, let's get into the clumbing, the waste systems. Because for most mammals, that's where the biggest water loss happens. The camel's abilities here are famous.
They are. The camel is just a marvel of retention. First, like we said, its nose is a dehumidifier. But second, its kidneys are masters of concentration. They produce this incredibly syrupy urine, and its feces are so dry they can be used to start a fire almost immediately.
And its tolerance for water loss is just, it's off the charts.
It is. It can lose up to 30% of its body weight in water and be fine. No circulatory collapse. That level of dehydration would be fatal for almost any other mammal.
But reptiles and birds, they have an even more elegant solution, a really old evolutionary trick for getting rid of waste.
Absolutely. So we mammals have to excrete nitrogenous waste as urea. And urea is soluble, which means you need a lot of water to flush it out of your system.
Right.
But reptiles, snakes, birds, they excrete it as dry solids, as urates or uric acid.
Which requires almost no water at all.
Virtually none. It is the ultimate water-saving adaptation.
And this brings us to this amazing aha moment from some recent research into, of all things, snake waste.
It sounds incredibly niche, I know.
But the implications for human health are huge.
They really are.
Yeah.
So here's the connection for you. In humans, high concentrations of uric acid are toxic. When those crystals build up in your joints, they cause the agonizing pain of gout
Or they form kidney stones.
or painful kidney stones.
Yeah.
So we struggle to get rid of it safely.
So how do snakes and lizards handle this massive crystal load without getting blocked up or being in constant pain?
Well, researchers analyzed the solid urates from over 20 species of reptiles, pythons, boas, and they found the urates aren't just random clumps of waste.
They're structured.
Highly structured. They're these tiny, textured spheres, just 1 to 10 micrometers across. And these spheres are themselves made of even smaller uric acid and water nanocrystals.
Nanocrystals. So it's a structural solution. They're not just excreting a toxic powder, they're engineering it into a safe, organized shape.
Exactly that. They've evolved a mechanism to safely package and eliminate this crystalline waste. And if we can understand how they form these tiny, non-toxic spheres,
It could change how we treat gout and kidney stones in people.
fundamentally, it's a perfect case of biological engineering informing clinical medicine.
That is a stunning connection. To think that the secret to treating a human disease could be hidden in snake pee. Okay, let's shift gears completely from internal chemistry to external physics.
To fluid dynamics.
We've seen how biology minimizes water loss, but some animals literally just pull water out of the air.
And for that, we have to go to the Namib Desert and talk about some beetles. Specifically, O. unguicularis and O. bicolor.
They live in one of the driest places on Earth.
And they rely entirely on windborne fog. They've adopted this counterintuitive strategy called fog basking. They just climb up the sand dunes and lean their backs into the wind.
They're acting like little solitary collection units. But from a physics standpoint, that shouldn't work. Trying to catch tiny fog droplets with a body that's a centimeter wide,
Wow.
the air should just flow right around it, taking the droplets with it.
That's the classic physics problem, right? The deposition efficiency is theoretically almost zero. The Stokes number is extremely low. It's like trying to catch mist with a tennis racket.
So they shouldn't be catching water, but they are. They must have figured out a way to manipulate the airflow around their own bodies.
They did. And the research uncovered this brilliant two-scale solution. It's pure engineering. First, you have the macroscale features.
These are the visible bumps and ridges on their backs.
Yes. And those features create what scientists call inertial traps.
Inertial traps.
By creating these sharp ridges, they force the streamlines of air to make a sudden turn. But the tiny water droplets, because they have inertia, they can't make the turn that fast. They lag behind.
And they slam right into the beetle's shell.
They crash right into the surface.
Yeah.
The beetle is literally forcing the water to miss the turn.
And that actually works.
It increases the droplet capture probability by almost 400%. The big picture geometry does all the heavy lifting of the initial capture.
Okay, so that's step one. But then you have to keep the water there. That's the microscale part.
Right. The microscopic features, these tiny bumps, just 1 to 50 micrometers in size, they deal with the droplet after it hits. They create enough texture to prevent it from sliding or rolling back off into the wind.
So it can join with other droplets and form a bigger drop that they can actually drink.
Exactly. It drains right down to their mouth parts.
And what's amazing is that the research showed that the geometry is the key, not the surface chemistry. I remember they coated the beetles' backs in nail polish to smooth them out.
And the water capture efficiency just plummeted.
It proves that the physical engineering of the shell, the shape, and the texture is the whole trick.
They evolved to solve an impossible fluid dynamics problem using only geometry. It's incredible.
This whole deep dive just shows that survival in these extremes is never one simple trick. It's this complex network of strategies.
Molecular stabilization, metabolic shutdown, chemical mastery over waste, and even, harnessing the laws of physics.
And as we close out, I think we have to talk about the absolute peak of biological resilience, the creature that really defies almost every rule we have for what life requires.
The tardigrade.
The tardigrade, the water bear. It's the champion of cryptobiosis, a metabolic shutdown so complete it makes estivation look like a light nap.
They can survive the vacuum of space. Temperatures near absolute zero. Intense radiation, total dryness. It is truly life at the limit.
And its secret is, once again, down to proteins.
Unique proteins. There's one called D-sup, a damage suppressor protein, and a group called LEA proteins. When the tardigrade dries out, these proteins form a protective glass-like state inside its cells. It's called vitrification.
They turn their insides into biological glass to protect their DNA.
That's essentially it. They lock everything in place so it can't be damaged.
And this research, inspired by these tiny organisms that defy the need for water, it's informing huge fields of science.
Oh, absolutely. It has implications for aging research, for finding ways to preserve human tissues and organs for longer periods.
And it even gives a little support to the panspermia theory, the idea that life could travel through space.
It really makes you wonder, what else can we learn from organisms that have evolved to just completely ignore what we consider the basic, non-negotiable requirements for life, like water?
They prove that the biological playbook is far stranger and far more adaptable than we ever could have imagined.